The ideal gas law. The ideal gas law combines Boyle's law, Charles' law, and Avogadro's all into a single law. A thing that's different about the ideal gas law is that it applies to a single set of conditions. All the other laws, including the combined gas law, things were changing, right? The pressure was changing, the volume was changing, and we were seeing what happened to the other things. The ideal gas law is looking at a sample of gas under a certain set of conditions. And so the ideal gas law is PV equals nRT. And sometimes students say PIV-NERT to help them remember what it is. So this is PIV-NERT. PIV-NERT is one of my favorite equations. So we're familiar with the P, pressure, volume, N we just learned about, and T is temperature, and now we've got another letter in there. It's R. R is a constant. And we could go through all the math, but we're not going to. If you want to see the derivation, I'll be happy to do it for you individually, but most people don't care, so we won't waste class time on that. But this constant, the value of it is going to depend on the units, but these are the units we're going to use. So 0.0821 liters times atmospheres divided by moles times Kelvin. Kind of a messy unit there. But this is telling us what units we need to use for the other variables. We have to have pressure in atmospheres because that's what's in this constant. Volume has to be in liters. Amount of gas is in moles. We were going to do that anyway. Temperature in kelvins. We were going to do that anyway. So there's PIV-NERT and the ideal gas constant. This is a table from your textbook that shows all these different laws and how they all tie together. So I don't really have anything else to say about that. Let's do a problem with the ideal gas law. Calculate the volume occupied by 0.845 moles of nitrogen gas at a pressure of 1.37 atmospheres and a temperature of 315 Kelvin. So we read through the problem. And then what have we been doing? We make a table. Let's make a table. That is a pattern, a method of approach that always works. We'll find that it'll work a little differently here, but it still works. So we'll do just the same as we've been doing, a table. First number, we write that in, 0.845 moles. And we ask ourselves, which of those variables is moles? P, V, N, R, or T? It's N, right? Number of moles. The next number we come to is 1.37 atmospheres. Well, atmosphere is a unit of pressure, and it says pressure of, so maybe that's a pressure. I think so. Got another number, 315 Kelvin. Should we convert that to Celsius? No. We always converted Celsius to Kelvin. This is the temperature. And how thoughtful of them. They put it in Kelvin for us. Wasn't that nice? Occasionally, they're nice. We ran out of numbers. We don't have any numbers on the second row. Is that a problem? Not necessarily. Let's think about this. That's a P, by the way. Oops. Now it looks less like a P. Let's fix that. P. Well, what are they asking us to find? Volume. Is there an equation that has N, P, T, and V for volume in it? There is. It's the ideal gas law, PIV-NERT. PV equals nRT. So we didn't really need a second row in our table, did we? Does it hurt that we made one and didn't fill it in? No. It helped us to identify what our numbers are, and so that we could look at it and see where we need to go. So PV equals nRT, we're solving for the volume. One of the nice things about pivnert is it doesn't have any fractions in it. Isn't that nice? So we don't have to cross multiply. We can just start rearranging. We want n by itself. So we'll divide by r, so the r's cancel. We'll divide by t, so the t cancels. And then we have to do the same thing on the other side. It's like with Tommy and Michael. If you give Tommy a piece of pie, you have to give Michael a piece of pie. Yes?
Why do you want n by itself? Is it n the most?
That's a really good question. I am solving for the wrong unit. Thank you. Okay, rewind. I don't know. That's farther than I wanted to go. Let's see. R, T, okay. We don't want that. Okay. Yeah. Thank you. We are not solving for n. I don't know why I was doing that. We're solving for v. Okay. So we're going to divide by p. I can't believe I did that. Yeah, I can. Is that better? Yeah. You know, sometimes when it looks like I'm doing crazy things, I actually am doing crazy things, so stop me. Volume equals nRT. Is it spring break yet? Over P. So what's N? N is 0.845 moles. What's R? That's that constant. It's always the same. So look it up. You might accidentally memorize it by using it so much, but it couldn't hurt to write that on your 3x5 card for the exam. Liter atmospheres per mole Kelvin, and then our units, our temperature, 315 Kelvin, and then we're dividing by pressure, 1.37 atmospheres. Before you calculate, check the units. Okay, so we've got moles and moles, those cancel. Kelvin and Kelvin cancels. Atmosphere and atmosphere cancels. Nice. We're left with liter, a unit of volume. Now we can calculate 0.845 times 0.0821 times 315 divided by 1.37 equals, my calculator is showing me 15.951 blah blah blah. I want that in 3 sig figs. I'm going to keep the 9. The first number I'm dropping off is 5 or greater, so I round the 9 up to a 10. That makes the 5 round up to a 6. Sometimes students have I don't know, they got like a philosophical issue with stuff like this. It's like your odometer rolling over is what it's like. 16.0 liters. That's the volume. Any questions? In some ways, the pivnert, the ideal gas law, is easier because you don't have all these 1s and 2s. And there's not a fraction in the equation that you have to get rid of right away. But you do have to remember to go look up that ideal gas constant. Here's another problem. A sample of gas has a mass of 38.8 milligrams. Its volume is 224 milliliters at a temperature of 55 degrees Celsius and a pressure of 886 torr. Find the molar mass of the gas. What? This isn't like those other problems, is it? Molar mass? We didn't talk about that. Hey, don't be alarmed. Think. What is molar mass? The mass of 1 mole, right? So if we had a sample maybe that wasn't necessarily 1 mole, how could we calculate the molar mass? It would be equal to the mass of the sample in grams, right? Divided by what? Avogadro's number, you're on the right track. But we're not talking about numbers of atoms. Molar mass, what are the units of molar mass? Grams per mole. So we're going to divide by the number of moles. And that will have the unit mole. Because when we calculate molar masses from the periodic table, we add them up and it's always 1 mole equals this mass. But what if we have some random sample that's not exactly 1 mole? And we know the moles and we know the mass. Well, we just divide and we can find the molar mass. You guys with me on that? So to find the molar mass then, we need the mass of the substance and we need the number of moles. Are either of those given to us? They give us the mass, but not in grams, right? It's in milligrams. Well, could we fix that? Sure we can. 38.8 milligrams. So we're going to multiply by grams, divide by milligrams. Chapter 2 stuff. If it's still not clear, it's not too late. Okay, we're still going to be using that. Milligrams are going to cancel. Then we ask ourselves, what does milli mean? 10 to the minus 3. So milli's on the bottom. We want to write what it means on the top. 10 to the minus third. To do that in your calculator, it's 1 times 10 to the minus third. So we do the math and we come up with 0.0388 grams. What I've written out here is not the only way to convert that. It's just me being consistent with what I showed you. If you can do it a different way, great. There we've got the mass. Ugh. So up here, the mass is 0.0388 grams. We need the moles. Well, what are all these numbers they gave us in here? Let's write them down and see what they are. Do you want to make a list or a table? List. Let's make a list. Okay, so the first number we come across, 224 milliliters, volume is. That translates into V equals 224 milliliters. Volume equals 224 milliliters. Next one, temperature of. Temperature equals 55 degrees Celsius. What should we do to Celsius? Change it to Kelvin, do it right away. Plus 273. 55 plus 273 equals 328. And the last number, 886 torr, that's the pressure, right? It says pressure. P equals. What we're looking for, number of moles, is N, right? We're looking for N. We've got V, T, and P. What equation do we need? Pivnert. The ideal gas law, Pivnert. PV equals nRT. What are we solving for? N. I think I was thinking of this slide or something. I don't know what I was thinking. This time we are solving for N. The number of moles. Divide by R, divide by T. Those guys cancel out. Do the same thing to the other side. So N equals PV over RT. We've got R in there. R says we have to use particular units. Let's see where I can write this. The units R equals 0. Oh, you know what? I could put it at the bottom. That would make more sense. R equals 0.0821 liters times atmospheres divided by moles times Kelvin. We need to convert some things, right? We could put them in the equation and then worry about it, but it's easier if you think of it ahead of time. So the volume needs to be in liters, and we've got milliliters. So we need to fix that. So we're going to end up, I'm going to erase this so that I have a little room. We're going to multiply by liters, divide by milliliters. Milli means 10 to the minus 3, so we're going to stick that there. And when we do the math, we come up with 0.224 liters. I'll put a circle around it because it's kind of messy in there. Volume in liters. The temperature's okay because we already fixed that. Pressure needs to be in what unit? Atmospheres. Nice thing about pressure units is it's always going to be one conversion. You're going to multiply by atmospheres, divide by torr, go to the table, look at the numbers. In front of atmospheres is 1. 1 atmosphere. Does anybody remember the number for torr? 760. 760 torr is the same as 760 millimeters of mercury, and both of those equal 1 atmosphere. So, 886 divided by 760, bless you, 1.17 atmospheres. So there's that guy, and we've got this guy. Can I fit them? I think I can fit them all in here. So the pressure, 1.17 atmospheres. The volume, 0.224 liters. Divide by R, 0.0821 liters atmospheres per mole Kelvin. And the temperature goes down there too, 328 Kelvin. Look at the units. ATMs cancel, liters cancel, Kelvins cancel. What I'm left with is 1 over moles, which ends up being equal to moles. 1.17 times 0.224 divided by 0.0821 divided by 328 equals N equals 0.00973 moles. Did anybody else get that number? It looks like the number I got this morning. Sometimes we come to the end of something like that and they're like, phew, we're done. No, we're not done. That was an intermediate number that we needed. What should we do with this? We need to go up here. right? We're trying to find molar mass. So this is where we have to have some attention span and remember what we were trying to do. 9.773 moles. 0.0388 divided by 0.00973 equals 3.99 grams per mole. So there's our answer. Is that a reasonable value for a molar mass? Is it possible? Yeah. What's the smallest molar mass that could be possible? What's the smallest atom? Hydrogen is the smallest, right? If you had hydrogen atoms, you could have 1.01 grams per mole. So anything smaller than that would be wrong. What's the next largest element? Helium. Helium is 4.00. What do you suppose this gas is? It's probably helium. Yeah. Any questions? This problem is an example of pulling together several different things into one problem. And so you're going to see some of that in the homework. You're very welcome to ask me questions, but try. Try it yourself first. Try to puzzle through it. And sometimes you have to struggle with it a little bit and leave and come back to it. And then sometimes it'll click. If it still doesn't click, then ask me. The ideal gas law is great. It works under a lot of conditions, but it doesn't work all the time. And this is because of what the gases do. And it's related to kinetic molecular theory. And we said that kinetic molecular theory does not explain gas behavior all the time either. On the left, we have a picture of ideal gas behavior corresponding to the kinetic molecular theory. And remember we said the particle size was small compared to the space between the particles. The interactions between the particles are insignificant. Looking at this picture reminds me of Wyoming. We've driven through Wyoming a couple times on our way to Minnesota. Wyoming is a decent-sized state, and it's not as big as California. Do you know what the population of the entire state is? It's about 400,000. That's the size of Fresno without Clovis. In a whole state. It's not very many people. There's a couple of sizable cities. There's Cheyenne and there's Jackson and I think Laramie maybe? I forget. Around Yellowstone. But there's a lot of just empty space. If you drive through there at night, you can drive for miles and miles and not even see a light from somebody's farm. I mean, absolutely nothing. So, how does this remind me of Wyoming? Well, these gas molecules are like people who live in Wyoming. Now, the people are not spread uniformly throughout the state, but let's imagine that they are. 400,000 people spread out in this big state. They're probably not even within yelling distance of each other. They may not even be able to see another person. They are very spread out. Are they going to interact with each other? No. They're not even necessarily going to know the other person's there. And now you can imagine them running around, and yeah, they'll run into people occasionally, but not very often. The space between the particles is large compared to the size of the particles. The space in that whole state is large compared to the space that the people take up. So that's under high temperature and low pressure. If we decrease the temperature, the particles are going to move more slowly. If we increase the pressure, we're going to squeeze those particles together. So now let's take those people in the state of Wyoming and gather them up into an area the size of Fresno. Are they going to interact with each other more now? They're going to see each other, right? Because they're going to be closer together. The particles of gases, when they're closer together and when they're not moving as quickly, are going to interact more, and the interactions become significant. Kinetic molecular theory does not explain what happens with gases when those interactions become significant. Think about maybe two Velcro objects. And if you take two Velcro balls, one with loops and one with hooks, and you put them together slowly, they're going to stick, right? But if you hit them together very quickly, the little loopy things don't have time to grab on. When the particles are moving fast is over here, and they bounce into each other, they just bounce off and they don't have time to react. Over here, when they're moving slowly and they run into each other like gases do, they have time to interact and it affects their behavior. So that's about all we're going to say about that.